Hello everyone, I am Dr. Siddheshwar Chopra and today we learn about Heisenberg's uncertainty principle, which is a very important topic of wave mechanics. Heisenberg uncertainty principle is basically, it states that it is impossible to determine the position and momentum of a particle simultaneously with unlimited precision. In other words, the more precisely one of the quantities is measured, the less precisely the other is known. So as you can see in the diagram here, if a person wishes to measure the motion of an electron, and which has to be done using some incident photon. Now the particles are quite similar in size, similar in nature, and the incident photon is impinging on electron here, which is already moving in some direction. After the collision, when the incident photon has collided with the electron, there will be some scattered photon and recoiling of electron occurs, which actually changes the state of measurement. The uncertainty principle is significant only at the atomic scale due to the small value of h. This is a very important point. Hence, it clearly indicates that the smaller the particle being observed, the more significant the uncertainty principle is. Now, its different forms are represented as follows. The first form is delta x delta p greater than equal to h cross by 2. Now, delta x and delta p are the uncertainties in the measurements of linear momentum and position. Say, if we make any measurement and we have, say, position measurement, which is x, it can be written as some x plus minus delta x. So delta x is that error, that uncertainty we are talking about in the measurement of position. Same holds good for the linear momentum also. Now, h cross is a new constant you are learning here. H cross is called a reduced Planck's constant, which is nothing but h by 2 pi. Also note that E is equal to h nu. So in terms of the reduced Planck's constant, I can write it as h cross omega, and P, which is the momentum, which is equal to h by lambda. In terms of K and h cross, it will be h cross K. So these are the new formula you have to understand in terms of the reduced Planck's constant. The second form of Heisenberg uncertainty principle is delta E and delta T, which is greater than equal to h cross by 2. Delta E delta T is greater than equal to h cross by 2, where delta E and delta T are uncertainties in the measurements of energy and time. Now, what are the applications of Heisenberg uncertainty principle? The applications are many, but we'll be, for example, here doing only the first one, which is highlighted in red, that is in proving the absence of electrons inside the nucleus, and other applications being in finding the ground state energy of the hydrogen atom, in finding the ground state energy of an harmonic oscillator, finding finite width of spectral lines. That means spectral lines cannot be measured to be infinite with the infinite accuracy. There has to be some finite width associated with the measurement of spectral line width. So let us go with the first proof, that is in proving the absence of electrons inside the nucleus. Let's assume that electrons do reside inside the nucleus. So let's start with that assumption. Then if this is the assumption, we know that the diameter of a nucleus is of the order of 10 to the power minus 14 meters. Hence, the uncertainty in the position, which is delta x of the electron, will be at max 10 to the power minus 14. Okay, that is the order of the uncertainty, that is your delta x. Applying the uncertainty principle now, we can take delta x delta p to be equal to h cross. Usually we take h cross, or in some books you find also h cross by 2, but it's okay. So the order of the answer means to us. So let us take delta x delta p equal to h cross. The uncertainty in the momentum delta p can be calculated now because we know the delta x. So we can find delta p, which is h cross by delta x, which comes out to be 1.054 into 10 to the power minus 24 kg meter per second. Now, if delta p is this value, then the momentum itself must be at least comparable in magnitude to the uncertainty in the momentum, or p is greater than equal to delta p. Thus, we can also say that p is almost equal to 1.054 into 10 to the power minus 24 kg meter per second. At least it should be equal to this value. So we know now what is the relativistic formula of the kinetic energy. That is nothing but total energy minus rest energy, which is m naught c square, and total energy is mc square. So I have the kinetic energy is equal to root of p square c square plus m naught square c4 minus m naught c square. Now this formula, root of p square c square plus m naught square c4, was learnt in the special theory of relativity earlier, or the relativistic mechanics. Now this value comes out to be almost equivalent to 19.4 mega electron volts. We know m naught, that is the rest mass of the electron, c is the velocity of light in free space, and p is the value we have just now figured it out. Thus the kinetic energy of an electron with rest mass, which is 9.11 into 10 to the power minus 31 kg inside the nucleus, is 19.4 mega electron volts. But the experimental results have shown that the electrons are emitted from the nucleus with kinetic energy of about 1 mega electron volt, which is much smaller than the one calculated using the Heisenberg Uncertainty Principle. Hence, this calculated value is in contradiction with the experimental value, suggesting that our assumption of electrons confined inside the nucleus was wrong. So it can be concluded safely that electrons do not reside inside the nucleus. So that is all for today. Thank you.